So what if the network that connects our entire world could actually think for itself? I mean, what if it could see problems coming, fix itself in real time, and get smarter with every bit of data it processes? Well, that's not science fiction anymore. It's the future that's being built right now with AI and machine learning. And it all starts with tackling this one huge, growing challenge.
Think about it. Every video you stream, every call you make, pretty much everything you do on your phone relies on this massive, invisible mobile network. But as we're pushing into 5G and beyond, these networks are becoming so complex, so dynamic, that trying to manage them by hand, it's not going to work anymore. The reality is, having engineers manually hunt down every single issue or tweak settings across thousands of cell sites, it just doesn't scale. It's way too slow, it's expensive, and honestly, in a network that's changing every millisecond, it's a losing battle. The only way forward is to stop reacting to problems and start intelligently automating the solutions.
And that brings us right here to what you could call the Smart Network Challenge. See, the goal isn't just to build bigger networks, it's to build smarter ones. And the key to unlocking all that intelligence? It's not more hardware. It's a totally new way of thinking. And it's powered by machine learning. So how does a network actually get smarter? Well, it learns. And, just like people, it can learn in a few different ways. So we're going to dive into the three big ones, the three fundamental types of machine learning that are completely changing the game for mobile networks: supervised, unsupervised, and reinforcement learning. All right, first things first, a quick definition. Machine learning, or ML, is really the engine behind most of the AI you hear about. And here's the most important part. We're not sitting there writing a rule for every single possible thing that could happen. No way. Instead, we give the machine a model, we feed it a ton of data, and we let it figure out the patterns, getting better and smarter all on its own. The first approach is called supervised learning. And honestly, the flashcard analogy here is perfect. You show the model thousands, maybe millions of examples where you already know the right answer. So you might show it data and say, hey, this set of network conditions, that led to a dropped call. After seeing enough of those flashcards, the model learns to spot the warning signs and predict when a call is about to drop so it can do something to prevent. And this visual just illustrates the process perfectly. You feed the model labeled data. This is a square, this is a triangle, this is a circle. The model chews on all those examples. Then when you show it a new shape it's never seen before, it can accurately say, oh, that's a square. Or in a network's case, hey, that looks like a high congestion situation, we need to do something about it. But what if you don't have all that nicely labeled data? What if you just have a giant, messy pile of information? That is where unsupervised learning comes in. You give the model all this chaotic data and just tell it, find the interesting stuff. It's kind of like being told to organize a super messy room with zero instructions. You just start grouping similar things together, right? You'd create your own order out of the chaos.
Now, what's really cool about this slide is how you can see that process in action. On the left, you've got all this raw, scattered data. On the right, an algorithm like k-means has gone in and automatically found the natural groupings, the distinct clusters. For a network, this could mean finding groups of users who all stream video the same way, or finding cell towers that have similar performance problems, all without a human ever telling it what to look for.
And finally, we've got reinforcement learning. This is where the system learns by pure trial and error. An AI model, which we call an agent, takes an action in the network. Let's say it adjusts a cell tower's power. If performance gets better, it gets a little reward, a digital pat on the back. If things get worse, it gets a penalty. Do that millions of times, and it eventually learns the absolute best strategy to get the most rewards. This classic diagram just makes it all so clear. The mouse is our AI agent, the maze is the network environment, and the cheese? That's the reward. The agent takes actions, turn left, go straight, it sees what happens, and it slowly builds a mental map of what works until it finds the fastest way to the cheese, or in our case, the most efficient way to run the entire network. Okay, so we have these super powerful ways for a network to learn, but where do they actually live? How do they plug into a real live network? Well, that's where ORAN comes in. ORAN, or the Open Radio Access Network, basically provides the standardized architecture, the playground, if you will, where all this network intelligence can come to life. So the ORAN framework has four key parts. First, you've got data collection, which is like the nervous system, pulling in information from everywhere. The ML training host, that's the gym, where the models go to train and get smart. The ML inference host is the main stage, where a fully trained model is live, making predictions. And finally, the actor is the muscle that actually carries out the model's decisions and makes changes in the network. Now here's a really critical question for any smart system. How fast can it react? In a mobile network, some decisions are strategic and can take a few seconds. Others need to happen in the blink of an eye. In ORAN, the answer to how fast you can react all comes down to where you put the AI's brain.
And this diagram shows you exactly what I mean. Now don't get lost in all the boxes here. Just focus on the main idea. On the left, you see the timing requirements, from over a second for slow, heavy-duty decisions, all the way down to less than 10 milliseconds for things that have to be instantaneous. And on the right, you see how ORAN physically puts the intelligence in different places to hit those speed targets.
You know, the easiest way to think about this is like your own brain. Some thoughts are slow and deliberate, like planning a vacation. Others are lightning-fast reflexes. ORAN's control loops work the exact same way. The non-real-time loop handles the big-picture stuff, like training a brand-new model from scratch. The near-real-time loop manages quick adjustments, like steering traffic between cells. And the real-time loop? That's pure reflex, making split-second decisions right at the radio.
So we've covered the what and the where of network AI. Now let's follow the entire journey of a single machine learning model, from just an idea on a designer's screen all the way to becoming a living, breathing part of the network.
Okay, I know this diagram looks a little busy at first, but trust me, it tells a complete story. This is the entire life cycle of an ML model. Think of it like a factory for producing and deploying network intelligence, and we're about to break it down step by step.
Here's that story. It all starts with a modeler designing the model. Then, it gets trained on tons of real network data. Once it's ready, it gets stored in a catalog and packaged up into a neat little application. That app is then deployed to run in one of those control loops we just talked about. But, and this is the really crucial part, it doesn't stop there. It's constantly getting new data from the live network, which means it can be retrained and improved over and over. It's a living system.
All right, so we've covered the theory, the architecture, and the life cycle. But what's the bottom line? What does all this complex tech actually do for you and me, the people who use the network every day? Let's talk about the real-world payoff. Now, just a quick technical side note on how these models get deployed. They can be packaged up in a couple of ways, as these self-contained images that are super flexible, or as files that allow for more custom-tuned efficiency. Both are used in the ORAN framework to get the AI right where it needs to be. Okay, now for the good stuff. And this is the most important part. This isn't just a research project or some theory on a whiteboard. The ORAN Alliance is actively designing and standardizing AI-powered applications that solve very specific, high-impact problems that you and I face with our phones every day.
So here's what all this amazing technology actually does for you. Imagine an AI model that recognizes you're watching a video and automatically optimizes the network just for that. Or one that predicts a cell tower is about to get overloaded and seamlessly switches your phone to a less busy one before your video starts buffering. It can even predict when you're about to enter an area with a bad signal to make your connection more stable. It means less buffering, fewer dropped calls, and just a much smoother experience for all of us. We are seriously moving from a world of reactive networks that get fixed after they break to proactive networks that can literally predict and heal themselves. They're learning to manage quality, traffic, and reliability on their own. The big takeaway here is that this is just the very beginning. And that leaves us with a pretty fascinating question. As our networks become truly intelligent, what's the next big thing they'll learn to do?